back, guys. Mr. J here, still in the home studios. We're going to continue on our IMF and molecular geometry unit, and today we're going to talk about Lewis structures. If you think back to pre-AP, we talked about Lewis dot structures when we talked about ionic compounds. We talked about how to draw the Lewis dot structure or Lewis dot diagram for a single element or single ion. This time now, we're going to expand that and move from a single atom into talking about how we can draw Lewis dot structure, Lewis structures for covalent compounds. So let's go ahead and get started. Okay. All right, so Lewis structure, if you remember, we talked about Lewis dot diagrams, shows the valence electrons, how they're arranged among atoms in a molecule. Remember, molecule, think covalent compound. Okay. In the valence compounds, remember, these are electrons that are found in the outermost shell. We're talking the S and P orbitals, okay? And we can tell the number of valence electrons by the group number if we look at our periodic table, or we just simply count from left to right and ignore our D block elements, okay? What these Lewis structures do is they reflect the central idea about the stability of a compound, and that it's related to the noble gas configuration. That is, that all atoms in a compound want to have a full valence shell, or 8 electrons. And so if you remember, here we go, and you simply count across, this is 1, right? Hydrogen's weird. We'll just call it 1 valence electrons, 2, 3, 4, 5, 6, 7, 8. And helium is weird, right? It maxes out at 2 because it only has s orbitals. It doesn't have the s and p, so that's why that is a little bit different. So we can use these Lewis dot structures to predict the number of bonds formed by most elements in their compound. Now, there are some exceptions to what we're going to talk about, and honestly, for us, I am not going to go into those exceptions. When you get into college, they'll definitely talk about some of these exceptions, but we're not going to worry about those. We're going to stick to the straightforward ones. Okay? And so when we draw these Lewis dot structures, they're going to consist of a chemical substance for an element surrounded by dots, and each dot is going to represent the number of valence electrons from 1 to 8. Okay? And so each electron we represent by a single dot. All right, if we look at carbon here, carbon has 4 valence electrons, nitrogen 5, oxygen 6, and chlorine has 7. Okay, so the number of dots, as we said, represents the number of valence electrons for it. What we see, these unpaired ones, like we see in nitrogen here, you got 3 unpaired and 1 paired electron. These are going to be used to predict the number of bonds that an element forms. So if we look at carbon, in theory, carbon can form 4 bonds. If we look at oxygen, oxygen has 2 unpaired electrons, so it can form 2 bonds, nitrogen 3 and chlorine 1. So that's going to help us draw these Lewis structures. Going back really quick, talk about the octet rule. Remember, octet rule says that atoms like to have a full outer shell of 8 electrons. They want to look kind of like their nearest noble gas. So then atoms tend to gain, lose, or share valence electrons to make this happen. Well, we're talking about molecules, so they're going to be sharing. Ionic compounds will be transferring. Okay. So what we know, if you remember back when we draw Lewis dot diagrams for metals, right, they have a tendency to lose their outermost electrons. We put the charge out here, whereas our nonmetals tend to gain them. Right, and our charge tells me how many electrons they gained. Also, we had the duet rule. Remember, that was for hydrogen and helium. I'll talk about that in just a second. So if we look at F2 here, fluorine has 7 valence electrons. Okay, so what's going to happen is when we form fluorine gas, okay, they're going to share a pair of electrons. So they end up sharing those 2 electrons there. And this way, this guy can count 2, 4, 6, 8. I'm happy. 2, 4, 6, 8. Happy. Both fluorines, to them it seems as if they have a full electron shell. Okay, and we represent that sharing of electrons by a single bond here. And this is kind of what we're going to be drawing. As I said, the duet rule, duet means 2. So for hydrogen and helium, they're going to be filled up when they have 2 electrons. Helium obviously is a noble gas, so it's not going to bond. But hydrogen, it doesn't need 8 around it to be happy. It needs 2, so it can look like it's nearest noble gas of helium. And we should once again show that bond, or that sharing of the electrons by a single dash there. All right, so let's talk about the steps for writing these. Here to to the right here is a Lewis dot structure. So first thing you need to do, you need to count up the total number of valence electrons from all the atoms. Okay, we can do that by the column that they're in. Secondly, we're going to use a pair of electrons to form a bond between each pair of bonded atoms. So you can see over here between nitrogen and chlorines, we have different bonded pair. And we're going to connect these elements with a single bond or single line to represent a single bond. Or remember earlier though, we talked about double and triple bonds, so we could actually have more than one line. Okay. Atoms, as I said, usually have a noble gas configuration. Okay. So what we're going to do is rearrange the remaining electrons to satisfy this. So each element wants to have a total of 8 valence electrons around it. Okay. Now, sometimes that doesn't work right. If we happen to run out of electrons before everybody has 8, that's when we got to introduce the idea of double bonds and triple bonds. That way they're sharing more. And we'll see some examples of that going forward. Okay, so once said, we're going to count up the valence electrons. We can use the periodic table to do this. So if we take water, for example, hydrogen has 1 valence electron, so there's 2 of those. Oxygen has 6, so we have a total of 8 valence electrons that we need to satisfy for this. Okay, so the second part, we're going to use a pair of electrons to form the bond between each. So we're going to put a bond between each hydrogen and each oxygen. Okay, so now if we look, hydrogen, this represents 2, right? Well, hydrogen's happy. It's got 2 electrons because it follows the duet rule. Same with this. Oxygen, however, only has 2 here plus 2 here, so a total 4. So we got to put in the remaining electrons. Well, we said we have 8 valence electrons. Okay, so we've used 4. Okay, so now we're going to put in 2 here. That gives oxygen 6, and then 2 more. Now everybody's happy. Oxygen has 8. Both hydrogens have 2. Okay, let's try the same thing with carbon dioxide. In this case, carbon's going to be our central atom. Carbon has 4 valence electrons. Oxygen we know has 6. Okay, carbon's going to want 4 more. There. Oxygen wants 2 more, so they're going to have to share. So if we attach one oxygen right here, we're going to have what? Oxygen have 2, 4, 6, 7. It's 1 short. Carbon has 2, 3, 4, 5. It's short. Do the same thing on the other side. Okay. But now if we put both of them, let's see. We got 2, 4, 6, 7 on that oxygen. 2, 4, 6 in carbon. 2, 4, 6, 7. So all our electrons are there. But the problem is everybody's not full. So this is when we have to go to doing double bonds and sharing more electrons. So what we're seeing, we're going to take this electron and move it over here. Okay. We're going to do the same thing for carbon, move it over there. So now look at, we're sharing 4 electrons. So 2, 4, 6, 8. That's happy. If we do the same thing on the other side, okay, boom, boom. Now look. Oxygen got 2, 4, 6, 8. Carbon's got 2, 4, 6, 8. Everybody has a full set. There's carbon's 8. Okay. There's oxygen's 8. And here's the other oxygen 8. Everybody is happy. And the only way we could do that by was sharing more electrons because a single bond didn't get everybody there. So we would write this here with lines showing the shared electrons, and then there's our lone pairs of electrons there. Okay, let's try a couple here. CH4, carbon has 4 valence electrons. Hydrogen has 4, so a total of 8 electrons. It should look something like this. HBr, hydrogen has 1, bromine has 7, so they're going to share 1 right there, HBr. Now, NO3 is a little different, guys, because it's NO3 minus 1 on your charges there. Okay, so we got to do a little thinking. Okay, nitrogen has 5, oxygen has 6. Okay, so 6, 18 plus 5. Plus, since it has a -1 charge, that means we're going to have to add 1 more electron to it. So for a total of 24 electrons. And so we're going to build that around the central atom of nitrogen, and we're going to split it out the side. Now you notice, to get this to work, we're going to have to put in a double bond. Now why do we put it on here versus here, here? We'll come back to that in just a couple minutes. But what I want you to do is to pause and try these 4 on your own. See what you can come up with. Don't cheat, please pause. This is very important for moving on to the next steps. So you got to be able to do this. So pause it Once you're done, come back. Waiting for you, waiting for you. Better pause it. Hopefully you did good. All right, here we go. So here's what OF2 would look like. Okay. Just put all these up and see how you did. Notice we got the triple bond in order to satisfy this because, right, only 2 there. 4, 6, 8. And then here we have a -2 charge there. So we're going to have 2 extra electrons once we get down there. And it should look something like this. So hopefully, if you didn't get these all correct, you can take a look and see where you went wrong. Okay, now let's talk about this. Why? Maybe you put your double bond here or here. It looks different, a little different to me. Well, that's okay, because this is something that we call resonance. So if we go back to the one we just drew here, okay, resonance is when there's more than one Lewis structure that can be written for a particular molecule. Like I said, I could put the double bond here or double bond here. And all that's different is where that double bond happens to be. And we call that resonance. Okay. The reason this happens is because we say that the electrons are delocalized, meaning that they can move around the entire molecule. So when there's more than one possible structures, okay, a lot of times what we'll do is we'll draw all 3 of them. Okay, so if we look at NO3-, it has a total of 24 electrons. There's 3 different ways we can write this. Okay, and so which one is it? Well, it kind of varies. Is there one drawing more correct than another? We'll get to that in just a second. Okay. And so these resonance forms aren't real bonding depictions. We don't know exactly for sure which one is going to be. Okay. The actual one is an average of these, meaning we got some way, some the other way. Okay. And so we can represent this by the resonance structure by showing the 3 different drawings. We can show how the electrons are moving around. Similar to that, you'll notice we got little charges here, and we'll talk about that a little bit later as well. Okay, but if you do have resonance possibilities, you do need to draw all 3 of those out. Okay, and so those arrows are showing how electrons can move. To figure out which of the resonance structures is probably the best or most likely, we use something called formal charge. And formal charge is the charge an atom would have if we are sharing all the electrons equally between all the atoms. Okay, and we use it to evaluate what we call non-equivalent Lewis structures or the resonance structures. Which one is the most likely to be correct? Okay, and what we see is that the atoms and the molecules really want to achieve a formal charge as close to 0 as possible. That's their goal. Okay, if we have any negative formal charges, those should be found on our most electronegative atoms, because those are going to have the strongest pull. So let's look at how we can determine the formal charge for an atom. Okay, when we look at these structures, we have a couple things we got to talk about. A bonded pair, this is where the electrons are shared between the atoms. We represent those as a line. Lone pairs are valence electrons that aren't bonded. They're not shared between atoms. Okay, so if we look at the fluorine example here, right, we have a bonded pair. Okay, that's going to be shared between them, but these electrons on the outside, they're going to belong strictly to whatever atom they belong to. Okay, so to calculate the formal charge, it's really easy. We take the number of valence electrons on a free atom. We can get that from looking at the periodic table. So minus from that the number of valence electrons assigned to that atom in the particular molecule by looking at the picture. Okay, and then finally, and the way we do that is this is a combination of those lone free pairs and half the bonded. Okay, so we want to assume that any lone pair, those are just the dots, belong entirely to the atom that we're looking at. Okay, and then the shared electrons or the bonded electrons are divided by equally. The way I do that is I just count a bond as 1 electron. It makes it a lot easier than worried about dividing equally. Okay, and so to calculate the formal charge of atoms, you're going to take the sum of the lone pair atoms, the dots, how many dots you have, okay, and 1/2 the shared electrons, or I just take the number of lines, so the number of dots plus line, and I'm going to subtract that by what their valence electron is. Okay, it's the easiest way to do it. We'll see some examples here in the next page. So let's look at this. Let's say we have, so formal charge is number of valence electrons minus the number of bonds. Okay, how many lines are there? Minus the number of unshared electrons. How many dots are there? So if we look at this compound here, okay, O3 ozone, we'll call it A, B, and C. Let's figure out the formal charge of each of these. So A here, oxygen we know has 6 valence electrons. How many bonds it has? It has 2 bonds, or 2 lines. So remember, they're shared equally. I just call it 2. Okay, it's 4 electrons, but it's 2 bonds, so I call it 2. And then we have 2 unpaired electrons, lone pairs there, and 2 here for a total of 4 non-bonding. So 6 minus 2 minus 4 is 0. Pretty simple. Let's do the same thing for B. Once again, 6 valence electrons, but now we have 3 bonds. We got 1, 2, 3. So I'm going to subtract 3 from there. And then I have 2 of these non-bonding electrons. And so 6 minus 3 minus 2 gives up a plus 1. Pause really quick and see if you can do C on your own. Okay, C, once again, 6 valence electrons. It's got 1 bond and then 6 non-bonding electrons, so it ends up with a charge of -1. So we got 0 formal charge here, plus 1 here, and then -1 there. Okay, so let's look at one more together. Okay, let's figure this out. Let's start with phosphorus. Okay, phosphorus has 5 valence electrons. Okay, it's got 1, 2, 3, 4 bonds. So 5 minus 4, and it's no unshared pair, so it's plus 1. Oxygen, on the other hand, 6 valence electrons, minus 1 bond, minus 6 non-bonding electrons gives us a charge of -1. How about the chlorines? Chlorines all look similar. So we get 7 valence electrons minus 1 for the bonding pair, and then we have 2, 4, 6 electrons, so it's 7 minus 1 minus 6 gives us a 0 on there. So it's not too hard. Let me have you go ahead and pause the video and try this one on your own. We're going to assign a formal charge to each of these. Go ahead and pause it now and then come back. All right, here we go. Hydrogen. 1 valence electron minus 1 here. For 1 pair gets 0. Oxygen has 6 minus 2, that gives us 4, plus 4 lone pairs gives us 0. Nitrogen, I think it's the one I did not. Nitrogen has 5, right? Minus 1, 2, 3, 4. And then there's no one pair, so it has, there we go, it's a plus 1. And then you can see oxygen here at 6 minus 2 minus 4, 6. And then here, 6 minus those 6 electrons gives 0, plus 1 more is -1. All right, hopefully this worked out for you. All right, so like we said, if these non-equivalent Lewis structures, these resonance structures occur, okay, the version that has the formal charge is close to 0, and with any negative charge on the most electronegative atom in there, are most likely going to be the resonance structure that predominates. So let's look at this. Pause this and see if you can write the formal charges for each of these. Get a little more practice in. All right. So we should have gotten something for oxygen, a plus 1 there. The carbon is going to be a 0. And then we'll have a -1 here. Excuse me. The second one, okay, we got our oxygen has a 0. Our carbon has a 0. And then our final oxygen has a 0. Look at, these are all zeros. That's what we're going for. So what we see is this structure is going to be the more correct one to draw out. It's the one that best describes how that's going to be bonded out. So that's kind of our winner there. Okay, let's look at this one. Okay, there are 3 possible forms. What we want to do is figure out which one is most likely. Why don't you pause this and see if you can do this one on your own and make a prediction. Is it going to be form A, B, or C? Okay, and pause me again. Come back. All right, so here we go. Form A, B, and C. So this is what you should have gotten for all these. I'm not going to go through those. If you have questions, you can email me on those. Okay, and then finally here. So if we look at them, okay, these two are fairly similar, 0, 0, and -1. This has a -2, -1, so lots of higher numbers on those. So we can immediately rule out form A. But B and C has similar charges. Well, Remember, we want if there's any negative value, we want it to be on the more electronegative atom. So who's more electronegative? Nitrogen or oxygen? Well, they're both in the same row, and oxygen is farther to the right, so our negative charge should be on our oxygen. So form C then is going to be the more likely bonding for this. All right, try this one on your own. Again, last one we're going to do. Try this on your own. Pause me here, and then we'll go through it really quick. All right, so here we go. Hydrogen has a formal charge, right? Hydrogen has one valence. Okay, it's sharing 2 electrons, which is 1 pair, so 1 minus 1 is 0. That's simple enough. Okay, and so the oxygen, then we move on to that, it has a 6 valence electrons, minus 1, 2 share pairs, so that's 4, and then it has 4 non-bonding electrons, so it's going to have a 0 on it. Okay, so we get a formal charge of 0 on that. Now if we go up to this next one, we got, once again, 6 minus 2 is 4, and then we got 1, 2, 3, 4 valence electrons there. Okay, so it's going to be, once again, it's going to be 0 on this one. And then finally, well, not finally, we have the oxygen at the bottom, right? 2, 4, 6. So 6 minus 6 is 0, plus we have 1 bonded pair, so this is going to have a formal charge of negative 1 there. Okay, and then finally we have nitrogen. Nitrogen has a formal valence electron to 5, and we have 1, 2, 3, 4. So 5 minus 4 is a plus 1. Okay. So hopefully that was pretty easy for you. Now, here's kind of the question. Okay. We put in our charge, which is a plus and minus. Okay. Are there resonance structures for this? And if there are, would it change, right? Could we move this bond down here? Would it still be this relatively the same? Okay. Maybe, why don't you try that one really quick and think about that. All right, guys. That wraps it up for this episode, talking about how to draw Lewis structures. Next thing we're going to move into is using these Lewis structures to determine the shape of a molecule. And this is what I've been telling you guys about all year, which comes down to pure memorization. So we'll get that on next time. If you have questions, guys, let me know, and I'll try to address those the best I can. Take care.